Well, we talked about iterators. And we're also going to talk about iterable. I gave you a heads up about that. But an iterator is just going to be an object that exists to iterate over some collection in whatever order we want, usually front to end. But an object that is iterable is an object that can return an iterator for itself. So these things are connected, but I want to clarify and be clear that they are separate things. So right now we're just talking about iterators. And again, just to give some motivation as to why we're going to care about iterators, we've got two different ways to iterate, to loop over a container. If the container's array-based, we're probably going to use it like that, I, starting at 0 to the length of the array. If we have a link structure, we're usually going to use a while loop that's going to be like, well, the current node's not null, do whatever, and then update with the current node references. Go to the next one. Two different ways to iterate over things. Now, to be clear, neither of these things are overwhelmingly complex. Neither of them are intimidating, whatever. But the point is, the way we loop over something depends on the underlying container. And that's not a really bad thing, but with iterators, we can eliminate the difference. We can make the way we loop over something the same. So iterator, like I said, an iterator is used to create an iterator object. An iterable is used when creating something one may want to iterate over. So we use an iterator for iterable things. Within the iterator interface, so to make an iterator, we implement the iterator interface. And if we go look at the interface, which if we click this, it shows us a couple of things here. But within this, we actually only care about two particular methods right now, the next and has next. These are the two we care about. They're the abstract methods that actually need to get implemented. Next just returns the next thing. And has next returns a Boolean indicating whether or not there exists another thing. This is probably really hard for you to see. Can you see this at the back? No? Well, if I zoom in, there. This is the actual Java docs. Go back to the course content. The two abstract methods we care about are next and has next. And if we have this, we can create an iterator object. And then I can say, well, the iterator has a next thing, process the next thing. And now we've got the same way to loop. When we're looking at this, all I know is that, okay, clearly I can get an iterator from this object because I called the iterator method which returned an iterator. That's what line 1 is saying. More on this later. But we get our hands on an iterator. This is that object that's going to help us iterate over some collection. And the way I iterate it is lines 3 through 5. Well, that iterator has another thing. Process it. Does it have another thing? Process it. Does it have another thing? Process it. This will run until has next returns false. So now, when you're looking at this, there is a class, or there's an instance called arbitrary iterable thing, right? We see on line 1. But you have no idea at this stage whether or not that arbitrary iterable thing's underlying container is an array or a linked structure, or who the hell knows what. You don't know. But the beauty of this is it doesn't matter. I don't care if it's a linked structure when looking at this code. I don't care if it's array. I don't care if it's who the hell knows what. All I know is I've got an iterator that does the iterating for me. It deals with that iterating logic. And that's how I use it. So this eliminates the need for me to even know what the underlying container is, which is pretty cool. Now, are there any questions at this stage? Yeah?
Could process be anything?
It could. Process is some arbitrary method or function, whatever, that's just taking an argument, which is the next thing. It's a stand-in for literally whatever. I could say print it out. It could be who knows what. That's all. To be clear, at this stage, it's still fairly abstract. I haven't shown you how to make an iterator. I haven't showed you how to like get the iterator. I mean, I guess I kind of did here, but we're working our way through it. As you can see, we've barely scratched the surface. So, although it's not required to know what the underlying container is when using the iterator, it is required to know what it is in terms, like if we're making one for that particular container. So we need to define the iterator for the underlying container. So if defining a collection that makes use of an array, we're going to want an array iterator. And we'll need to define this. And so we can make a new class, and this would be a brand new class. We make a new class, public class array iterator, and it implements the iterator interface. They're generic. This class is going to have three fields, size, element, and index. In this case, this is for an array. We are creating an iterator object that knows how to iterate over an array. Later, we'll make one that knows how to iterate over a linked structure. But these three fields, size, the number of elements in the collection, because remember, the length of the array and the number of the things in the array that we care about are different. So size, some array I'm calling here elements, that's going to be like the actual container of things that we're iterating over. That's the array we want to iterate. And index, which is going to be the current index the iterator is at. Think about an array. What's it going to need to know how to iterate? Well, where it currently is in the array, where it currently is in the array, and where do I stop? That's what we're going to want. That's what this is for. Now here I've got a constructor. I wrote it like this. We really didn't need that exception. I just included it because it makes the code a little cleaner. It's a little more robust. But the array iterator keeps track, well, it takes two arguments. One, the array we want to iterate over, and the size. Because again, remember, size and length of the array are different. If size happens to be bigger than the length of the array, we'll raise an exception because something's wrong. I could have skipped this and just, it would crash later anyways, but I included this because why not? Right? Is the reason I have the exception clear? Yeah, cool, right? If the array is size 5 and I say your size is 107, okay, we got a problem. Otherwise, this elements is elements, this size is size, and the index we start at is 0. Now to be clear, I'm creating an iterator that starts at index 0 and goes to the end. Technically, I can make an iterator go in whatever the hell order I want it to, but typically you're going to start at one end and go to the other. This is very common. So the constructor just sets up the iterator. It says, okay, little iterator object, here's your array. Here's the size, and you start at index 0, and you're ready to go. But I haven't done anything yet. It just exists if I call this constructor. So it's just doing the setup like your average constructor. And then I have the method has next. Well, is the current index less than size? If it is, there exists another thing. Right? Makes sense. So it returns that Boolean. And then we have next. Well, if someone tries to call next when it doesn't have a next, raise the exception, no such element exception. Cool. Otherwise, get the element from that index, increase the index, and return the element. That's all. If this looks now I want to be clear. I'm not saying that this is trivial, but I'm saying if this code is overwhelming you, you're thinking too hard. It really is that simple. Not trivial, but simple. Where you might be having a hard time at this stage is connecting, okay, we're making this, but I don't really see how this gets used. We're working our way there. But any questions yet? Okay. So yeah, next returns the next element and updates the index. The way this is written, if next is called when there's no elements to retrieve, an exception is thrown. Note that the iterator can only go in one direction. Once the iterator object hits the end, it does not reset. It's useless. To start iterating again, make a new iterator. And like I said a moment ago, there's nothing preventing us from creating an iterator that goes in the reverse order. I mean, that's not, I'm going to say like 99% of the, I pulled this number out of my ass, but I feel like probably 99% of the time you start at the beginning and you go to the end. But you could say it could go in any other order you want. It's up to you. All right, warning. Consider that the array iterator has reference to the underlying array container. Here's what I mean. Look at the constructor. The constructor takes an array of elements. But it didn't really. It got a reference to an array of elements, right? So I have an alias. So think about like a stack. Imagine I had an array stack, and there's an array field. There's a field called stack. That's a reference to some array that contains the data. When I create the array iterator, I'm going to give it a reference to that array. So I have an alias here. And arrays are mutable. So this is a recipe for problems if you start screwing with your data. So what do? Don't screw with the data. Simple. Generally, iterators should not modify the collections they are iterating over. Side effects like this are a recipe for disaster, right? So I'm just saying, warning, this does create an alias. It's an alias to something that's mutable. And you could really start screwing things up in your code if you do that. So don't do that. But the good news is your iterators should not be modifying the contents of your collection. That's not really a thing iterators do. Technically, you could write code to do that, but don't. Any questions? So I only showed you the array iterator. I didn't even show you how to like create an instance where it comes up in the context of what we've already seen. And now I'm going to show you a linked iterator. So a linked iterator. This one's even easier, I'd say, because it only needs one field. The one field is, well, a reference to the current node. The linked iterator constructor just gets a reference to the current node, so the head node actually, the beginning of some collection, set current to head. Has next is, well, it's current null. And next is, get the return element, update what current reference is by just saying current u equal your next, and then return the element. It's the same general idea as the other one, except for linked structures as opposed to the arrays. So this is your linked iterator. A linked iterator is a separate class. It just exists somewhere else, okay? Now what's cool about this is this will work for any linked collection. The array iterator will work for any of the array-based collections we've used so far. But we've seen two iterator classes, one for linked structures, one for arrays. We can create an instance of either of these and loop over it by doing something like this. Ask the iterator that I created, regardless of whether it's a linked iterator or an array iterator. Because remember, they're both implementing the iterator interface, so the type of the reference variable for the iterator is just iterator. It doesn't need to be an array iterator or a linked iterator, it just needs to be an iterator. So I just say to the iterator, do you have another thing? Has next? Then do whatever the hell you want to do with it. Has next? Do whatever you want to do with it. Has next, and so on. No need for your typical counting for loop for indexing arrays or that updating of the link structure. No, that's already dealt with by the iterator. We just interface with the iterator. The iterator does the underlying work for the specific container. I interface with an iterator that just says, do you have another thing? Give me that thing. Do you have another thing? Give me that thing. Constructor has next, checks next, just like the array. Iterator, the iterator only goes in one direction. Once an element is retrieved with next, it's not possible to retrieve it again unless you create a new iterator. And warning, if the node class is an internal class, the linked iterator will also need to be internal too. Yes, that's a good point. So remember how we made, actually it's funny, I just said the array iterator class and the linked iterator classes, these are classes that exist somewhere else. It's entirely reasonable to have these be internal classes. Remember how we made the node class an internal class for our link structure? Well, same thing here, we could do that. And in fact, it would have to be if the node class was an internal class, because otherwise this wouldn't know what a node is. Everyone's okay, no questions, no nothing. You guys are either too smart or too tired. It's probably a little bit of both, right? Yeah, okay, fine. I don't know about you. For me, it feels like the last 2 weeks, I've been so goddamn tired. After the time change, I've been going to bed earlier. Even though the time change went the other way, it's like I'm going to bed 2 hours early now, and I'm still exhausted. I don't know what's going on. Holy moly. I need more sunlight, I think. And then I wake up and there's snow. It's new snow today. Oh my God. That was annoying. We're almost there though, right? We're almost there. All right, so collection iterator. So consider a sorted bag. We could be considering a stack or a queue or an index bag, whatever, but I'm saying consider the sorted bag. And do you remember the sorted bag interface? How there was a method in the sorted bag interface called iterator. Remember that? Yeah, it was there. And I said, don't worry, we'll talk about it later. Well, now we're talking about it. Now, we didn't include it in the stack or the queue. Really, we should have, but I didn't want to start talking about iterators at the beginning of the semester. So really, I would go and add those. But inside of that interface, there was a method called iterator that returned an iterator. Now, if we make an array sorted bag, do you think this iterator would return an array iterator or a linked iterator? Obviously. And similarly, if the implementation was a linked one, we're going to return a linked iterator. You return the specific type for the actual underlying container. But the point is, whether it's a linked iterator or an array iterator, it's an iterator because we implemented the iterator class. And the iterator method returns an iterator. So, if we have an array sorted bag, this is what our iterator method would look like. Public iterator, iterator, return new array iterator, bag, size. Why do I give it bag? Why do I give it size? Well, if we go and we look at the array iterator constructor, it needs a reference to the array, and it needs the size. So we gave it what it needs. And then this method goes and creates this new array iterator and then immediately returns it. If we had a linked sorted bag, this is what the iterator method would look like. Go and return a new linked iterator. This one only takes a reference to the head because that's all the linked iterator needed to do its thing. Since both versions of this class just need return an iterator, and since the iterator provides a common way to iterate over the container, it's possible to iterate over an array and link structure exactly the same way. This is basically exactly the same code I showed you up there a few moments ago, but now with the my bag. And again, when you look at this, okay, line 1, an iterator of integers called iterator mybag.iterator. Okay, mybag.iterator returns an iterator, so this is all good. And then we loop. Iterator has next, do your thing with next. Iterator has next, get the next and do your thing. Iterator, it's so on and so on and so on. Let me ask you, the mybag reference variable, was that for an array iterator or a linked iterator? Or pardon me, was that an array sorted bag or a linked sorted bag? Yes. Exactly. It doesn't matter. It doesn't matter. And that's the beauty of this. And I really want to impress upon you that like this really is like at this stage of the semester, we're starting to see how like Java's enforced rules that you have to follow, we can really start to see the value of it. How like, oh, this interface, what's the point of the interface? Well, look, it's an iterator. Yeah, but is it linked? It doesn't fucking matter. It's an iterator. Is it a linked iterator? Is it an array iterator? Doesn't matter, it's an iterator. And an iterator, if it's implemented correctly, I have next and next, has next and next. That's all I need. That's it. So it doesn't actually matter what the underlying container is. Remember I said at the beginning of the semester, and I've been saying throughout the semester, I really want to emphasize the difference between the what and the how. What? That's what I want to do. How does it actually work? That's on this side. I don't care. Again, I know we actually do care because we're building it. So we are operating on this side and that side. But the point really is that we have that boundary of the what and the how. I have an iterator to iterate over my stuff. How does it actually work? I don't care. I don't want to care. I don't want to know, because I don't need to know. I just need to iterate over this collection. Raise your hand if you used lists in Python. Of course you did. Raise your hand if you ever used like that for each loop in Python. Yeah. Did you need to know how it worked under the hood? Do you know if it was an array-based list or a linked-based list in Python? No. It didn't matter. In fact, did you even ask that question? No, because it didn't matter. You knew what you could do with your list. And it didn't matter how it worked at that stage. Sure, some of you may have gotten curious and thought to yourself, well, how does it work? Fine, you could ask that question, but you didn't need to. You just needed to know the interface. And if you used that for loop, you used an iterator. You just didn't even know. It's beautiful. So all of this like strong object-oriented design, we start to see where its value really starts to come up in all this like abstraction and everything. It's really nice. Any questions? I feel like this topic might feel kind of benign, but I always find it kind of like special because I feel like this is the point of the semester where things start to kind of come together in terms of why we were doing things this very specific ways when we could have done them other ways. But like interfaces, did we really need to do that? All of these layers of abstraction, we didn't really need to do that. You're right, but eventually it starts to come back together and you can start to see. It might not, you don't have a full picture yet. You won't have a full picture for a few years. But maybe things are starting to become noticeable. I think it's kind of nice. All right, so toString. Consider the following toString for some collection. You can't look at, okay, look, we create a string builder, we get an iterator. Well, the iterator has next, the builder.append, or iterator.next, append a comma, keep looping, and then in the end return builder.toString. Is this for an array collection or a linked collection? It doesn't matter. It's the same. We couldn't have done this before without an iterator. We couldn't, because if you had a linked implementation, you needed to use that while the current is not null. If you had an array base, you had for I equals 0. So now, this code is far more general. The code is going to be exactly the same for a toString regardless if you have a linked implementation or an array implementation. I really hope I have some equals examples too, because the equals is an even better example. I don't. Maybe I do down here. Yes, okay, we'll get there. I don't want to spoil the fun. All right, so that's all about iterators. We can actually take things a step further by specifying that our collections are iterable. If we can return an iterator for a specific collection, we can then say that our collection is iterable. And if our collection is iterable, we can take advantage of these fancy enhanced for loops, these for each loops. So what do I say? The iterator interface is used for creating an iterator object to iterate over something. If making a class that is to be iterated over, then the class will implement iterable. For example, asking the collection for an iterator, mybag.iterator. You would want your bag implementation to be iterable. And the iterable interface requires that we have one method, iterator, that returns an iterator. That's it. That's all we need. So we can make our class iterable by just having it return an iterator for itself. Now, if I have an array sorted bag, I'll return an array iterator. That's just an iterator. If it's a linked bag, it would be the linked one, fine. But all I have to do is make my whole class iterable and have this method included, which would look like this or like this, depending on if I had the array or linked implementation. That's all that's needed. Now my class is iterable. And if it's iterable, I can make use of these fancy for loops. For things that are iterable, we can use enhanced for loops, these for each loops. This is like what's default in Python, for each thing in a collection of things. That's what this is here. For type, reference variable, colon, iterable thing, process, the reference variable. That's like a generalized version of what the code is. But instead of saying something like creating the new iterator object and doing all this code, I can replace all of this with this. So I don't actually need to go and explicitly call the iterator method, create a reference variable to that iterator, ask that iterator if the next exists, and get the next. I don't need to do all that. I just need to do this. The reference variable type, integer. The name of the reference variable, I called it X. The name of the collection, my bag, process on X, where process is whatever the hell we want it to be. That's it. So we can even simplify this toString a little bit more. It's exactly the same as this, but I'm replacing all of this code with a for loop that looks like this. So it looks like this now. Now, this is where it brings us back to what we saw a few lectures ago. Typically, I'm laughing because I know how weird it's going to sound when I explain it, and it makes perfect sense, but I know it's not going to sound like it makes sense when I explain it. But it does make sense. Typically, I would write it like this. If I had, imagine in my main method, I had a bag object called my bag. This is how I would iterate over my bag. Okay, that's what I would do. Cool? You could do this with arrays too, by the way. Like arrays by default are iterable. But when we're using an array as a container, remember, the length and the size are two different things. So the default array iterator won't work for us. But this is how we would do it. We use the reference variable to my bag. And my bag is a reference variable to a bag of some sort. And the bag is iterable, so I can do this. If we're looking at this toString example, remember that this toString method would exist within the bag class. the sorted bag, the indexed bag, whatever it is. It's the toString. This toString exists within that bag class. So the previous example that I was just referring to, that was saying like, imagine I've got a reference to a bag in my main. Now I'm using some code that is within the bag class. Remember that the my bag was a reference to a bag, which is iterable. This, in the context of being within the bag class, this is a reference variable to a collection that's iterable. It's a bag, right? Right? So this is, yeah.
It's kind of like, well, in Python, if you create the getItem method, you can then index the object instead of having to index like the field that is the array that an object contains.
It's exactly the same thing. So this is a reference variable to a bag in the context of this being within a bag, the toStrings for the bag. Again, it doesn't matter if it's the sorted bag or the indexed bag or the linked indexed bag or the sorted array. It doesn't matter, which is kind of the beauty of all this. But this is the reference variable to the thing that's iterable, because the whole class is iterable, so this means iterate over that collection. Cool? I think that's pretty cool. So this is, if we go back to the previous topic, remember I was trying to explain this without giving you all the context of what iterator means? Well, now it's a little cleaner. I will say, if this isn't immediately obvious or immediately clear to you, you're probably pretty normal. I'm specifically talking about like the this, like wait, why is it this now? But this is not really a thing. Well, it is though. But if it's not immediately clear, just spend some time. You can go download this code that I give you and use it and play around with it. And a little experience, it'll click. So at the end of the day though, this enhanced for loop is just syntactic sugar for this. It means exactly the same thing. It's just nicer syntax for the same thing. Because look at the difference. That one, it's just this nice clean for loop. That's like Python's default for loop, for crying out loud. And then Java is, well, okay, get the iterator object, ask the iterator object if it has next in the while loop, and then you do it, and then you... One's, at the end of the day, they're both simple, fine, but one's a little cleaner. It's a little nicer syntax. That's all it is. It's functionally the same. It's just, at one point in time, the good people at Java said, maybe we can make this even cleaner, and they did. It's just an improvement of syntax. Questions, questions, questions? So, the equals that we used for the stacks and the queues in the past were absolute trash. They were garbage. Because I would only ever be able to compare array stacks to array stacks. I would never be able to check if to correctly check if a linked stack and an array stack were equal. The underlying container shouldn't matter. A stack is equal if the things are in the same order, right? They have the same number of things and they're equal all the way down. That's what it means for them to be equal. But I wouldn't have been able to do that before. Because, I mean, if you look at this one requires that this dot stack, well, that would have to be a full array, and that dot stack would have to be an array. I even had to cast this as an array stack. So, I mean, this is an array stack. It's not a stack, it's an array stack. So this really isn't that general. Similarly for the linked structure, right? I have this and that. I start with a this current, that current, and I go through each node in the link structure, compare that they're equal along the way. But what if one's an array? I can't iterate over an array as if it's a link structure, meaning it's not possible for me to tell if they're even equal. But I should be able to check if an array stack or a link stack are equal, because they're both stacks. I want to know if stacks are equal. I don't want to give a shit about if their underlying containers are the same. That doesn't matter to me, and it shouldn't matter. But the way this is implemented, or the way we implemented it, we had that limitation. And the whole cause of the limitation was caused by the fact that you iterate over one a different way than you iterate over the other. But we don't have that problem anymore. With iterators, we can iterate over these collections the exact same way, whether or not it's a linked stack or an array stack. You just need an iterator. So we could go back. We're not going to, but we ought to go back and fix this. Go, create iterators, and check if each thing is equal. Here, we can get away with line 18 by saying this iterator dot has next. I could say this iterator has next and that iterator has next. I could say that. But we've already established that they're the same size on line 13, so I didn't. Maybe I should just for cleaner code, I don't know. But now, I just use the iterator to iterate over the collection. And I check objects.equals, this current and, or sorry, this next and that next. But is this one for, do you think this equals is for, I mean, it's for a stack. Do you think this equals is for a linked stack or an array stack? Does it matter? No. And again, oh, this is beautiful. You can't tell from this code if it's a linked stack or an array stack, because all of the nuance, whether it was a linked or an array, is dealt with by the iterator class, by the iterator object. It doesn't matter. This can check if an array is equal to an array stack, a linked stack is equal to a linked stack, or a linked stack is equal to an array stack, or an array stack is equal to a linked stack. It doesn't matter. It doesn't at all. And this is amazing to me. This is just another example of what I was just talking about. It enables us to write, like all of this stuff that, I know when you start learning Java, it feels like there's a lot of rules Java has. And it's a kind of a pain in the ass. But I kept telling you along the way, like, you know, a lot of these rules, they might feel like a pain in the ass, but they actually like protect you along the way, right? And one of the earliest examples is just the fact that this is so strongly typed and you have to be so explicit about your types. You create a variable, what type is it? And just having that extra step there actually helps eliminate a lot of potential issues because, well, you know types are correct. Where with Python, you hope they're right. But that was just one example of a lot of like the rules and things we just do in Java. And this is now an example of like, and look how it comes together in the end. It forces you to write the code in such like a clean, consistent way. There are other languages that do this better than Java, don't get me wrong. But I don't know, I think this is such a great example of like, oh, now we can really see the value of all these layers of abstraction and interfacing with these different, interfacing with the nuance at the right level of abstraction that we eliminate. It's precise enough, but we eliminate any of the unnecessary nuance we don't care about like, well, was it an array or a link structure? It doesn't matter. It's some collection, and I want to iterate over it. It's beautiful. If you don't think it's beautiful, oh, there's something wrong with you, because I think it's quite nice. Any last questions about iterators and iterable? Yeah?
Sorry, in that last one, it said instance of in the third if statement.
Yep.
Could you just explain that?
So that's just an operator that checks, is O, is it even a stack? That's it. It'll return a Boolean. So instance of is an operator. It's not a function, it's an operator. It's a Boolean operator that takes two operands, the O, and in this particular example, the right-hand side operator was actually like a type, an interface type. I could have said array stack, like a concrete class, or like an interface, it doesn't matter. But if O is an instance of a stack, it returns true. If it's not, it returns false. So if O isn't even a stack, let's say it's a queue, let's say it's a country object, well, they're not equal then. A stack is not equal to a country. It just isn't. We could, in some weird world, maybe you really want that to be the case and you incorporate that logic into your code. But this is fairly general purpose equals code. Does that answer it well? Cool. Now, we always know that this, because right now the comparison is between like this and that comes from O. Right? So O and this. We always know that this is a stack. How do we know that this is a stack? It might seem like a stupid question because but I want to make sure this is clear. Exactly. This must be a stack because this is the equals method within some implementation of a stack. So it must be a stack. It can't not be. If it's not, well then we're not looking at an equals method from within the stack class. And then this equals wouldn't make any sense at all. Any other questions? We're good? Happy, sad? All right, exceptions. Now this particular topic is going to be fairly high level. You already have a reasonable understanding of exceptions in the sense that, like, what do we use them for? How do we throw them? We can create our own exceptions if we wanted, our whole new type. You just have to implement an exception. You don't typically do that though. But I'll just give you a little bit more context about exceptions with this topic. So exceptions provide a logical way to separate your regular code from the exceptional situation code. Now, I will also say there's a lot of programmers that think exceptions are terrible. They think they're a really bad system. And one of their arguments is, well, exceptions are like intrinsically, they're all side effects, right? Well, we don't like side effects. They're right, that's a good point. But in general, people were using exceptions whether you like them or not. They do provide a nice, easy way to propagate exceptional situation up the call stack to the appropriate thing. Because whenever an exception gets thrown, it either gets like caught and handled, or it doesn't get caught and it crashes your program. So think of, in 161, we talked about the call stack, right? Raise your hand if you know what I mean when I say that. One person. All right, so I think we get to that near the end of this topic. But every time, you know, you can have your main method, and then maybe your main method calls a method, that calls a method, that calls a method, that calls another method, right? So we're actually we're a couple layers deep, right? All of this is stored on what we call like the call stack. And when a method finishes, we pop that method off the call stack. It's literally a stack. I know, right? Yeah, see, you get it. So we've got this stack. But like, let's say, okay, this method called this method, that called this method, that called this method, and this method throws the exception. Where is that exception going to get handled? Because the exception gets thrown to the calling method, and if it doesn't get handled there, it gets thrown to here. If it doesn't get handled there, it gets thrown, and eventually it gets to the main method, and if nothing catches or handles it there, it throws it to you, the person who hit run, which is what you see when you see like array index out of bounds, because nothing handled that exception. Now that said, there are certain exceptions that you never try to handle, like array index out of bounds. You don't typically try to handle that because that usually means, well, someone effed up. The programmer screwed up. But there are some exceptions of like, well, what happens if there's a file I/O exception? It wasn't there. What do you want to do, right? It gets handled a certain way. So there are some exceptions we want to catch and some we don't typically want to catch. Yeah, and what's also neat is because like exceptions fall in like the class hierarchy, it actually allows us to get really like precise with like the types of the exceptions, which is kind of nice, and it gives us flexibility to like reflect the nuance of different exceptional situations. But within the Java hierarchy, we have like, okay, we have like the Java language, and within that we have objects, and within that we have throwable, and within throwable we have errors and exceptions. Errors, if you ever hit run and your program crashes because of an error in Java, you deserve a medal. They're very rare, and it's not your fault. That's like usually something went wrong with Java. Exceptions, that's like, well, what's happening with like the code and whatnot. So errors. And then within exceptions, we have two types of exceptions. We have runtime exceptions and other exceptions. So errors. There are two classes of throwable objects. A throwable one is that, we use the throw keyword. Errors are one of the two. Errors are typically for unrecoverable situations. You don't try to catch them. Something went wrong. They are very abnormal situations. You can't catch them, you can't handle it because it's not something you can resolve at runtime. Something's wrong with like the computer. Errors are regarded as unchecked for the purpose of compile time checks. To understand why these are not caught, like imagine like out of memory, right? Imagine your computer ran out of memory. So what are you going to do in your code to solve that problem? You ran out of memory, there's nothing you can do, right? Yeah. So that's really all we're going to talk about in terms of errors. Throwing an exception. Several methods written so far have thrown exceptions. Below is like the remove example. Ooh, hold on. Yes, remove first. Remove does not throw an exception, but remove first will if trying to remove from an empty bag. So here's like a sorted bag, remove. If you remove from a bag and it doesn't succeed, it just returns false. But if I say remove first is supposed to remove and return something of type T. But if I call remove first and there's nothing to remove, I can't return a Boolean because this method has to return something of type T. Returning null is an option, but not great because null is just this big ball that means nothing. So alternatively, I can raise this exception, I can throw this exception that has a little bit more information. No such element exception, empty bag. Oh, I know what's wrong. Where if I get null, was the thing at the beginning of the bag null? I could have added null to a bag. So getting null back isn't helpful. I don't know. So the exception's kind of needed here. So here's an example of throwing an exception. It's a no such element exception, which is a subclass of a runtime exception. It is an unchecked exception, so the method does not need to include a throws no such element exception in the method signature. Do you remember when we were doing the file IO stuff at the beginning of the semester when doing any reading? How in your methods you'd have to have like, remember how there were some exceptions that, remember when at the very beginning of the semester, in the first lab, when we were trying to like read from standard input, how we had to put that code in a try catch, right? Remember how we had to do that? There are some types of exceptions where you have to do that. Cool? And there are some where, well, you don't have to. That's the distinction there. And that's really all we need to know, is that there exists a distinction and we're good to go. The motivation for using exception remove first is one, well, we already said that. Either way, as the writers of array sorted bag, it's not possible to know how the user of the array sorted bag should address the situation if they try to remove first and there's nothing there. So what do? We raise the exception. One may wonder why the more general remove does not throw an exception. That's because the return type is, we've already talked about this, but it's a Boolean, so false is reasonable. And the expected return value of remove first is type T, the actual first thing in the bag. There's no obvious explicit way to communicate the failure. So one could return null or some other special value, but exception is more appropriate. And it also conforms to Java interface. Ultimately, however, it would not be wrong to have a more general remove, also throw the exception. These are all design decisions at this point. And we'll end it here. Any last questions? All right, I'll see you later.